All right, this is Andy Schweitzer, and now we're coming up on our last video for composition of solids. Now, I mentioned in the last video the difference between percent composition of an individual particle versus a larger grouping of substances. For example, you could say, like on the Earth, that we're standing here and we have our atmosphere that is surrounded by all these gases, and that would be usually about like 80% nitrogen, let's say 18% oxygen, and then let's say there's a minuscule 2%, although rising, carbon dioxide. So this would be the percent composition of the actual atmosphere. Okay. Now, what would happen if we were to say, okay, what is the composition of the carbon dioxide molecule? Okay, of the actual molecule, right? What is the actual composition? Okay. Now, this is the formula CO2. It is a ratio of individuals. Okay, it's a ratio. It means that there's one carbon for every two oxygens. And this is locked. So if I were to have a stack of a plate of a carbon dioxide molecule, I threw one on there, it'd be a carbon 1:2 ratio. If I stopped another one on there, all right, still the ratio would be 2:4. And it's still, so if I could stack a whole bunch of them on here, and no matter how many I stack up here, it's always, because the actual formula is locked, I'm always going to hold this proportion. So because of this formula being locked, my sample size, okay, it doesn't matter, okay, does not matter. So my composition of carbon dioxide for a 1 gram sample would be a certain percentage carbon, certain percentage oxygen. That would be fine. For a 10 gram sample, doesn't matter. 100 gram sample, same thing. Okay, I'd have 1:2 ratios. Now, because carbon has a certain mass, a locked mass, and oxygen has a locked mass, then the percentage mass carbon, percentage mass oxygen is also going to be locked, regardless of the sample size. So if I have a 1 gram sample, there's a certain percentage of that 1 gram will be carbon, a certain percentage of that 1 gram will be oxygen. Same thing for 10 grams, same thing for 100 grams, same percentages. Now, just because we have lots of numbers of oxygens versus carbons, twice as many, doesn't mean it has to be the same percentage for carbon as oxygen. Okay, each carbon has its own mass, each oxygen has its own mass. So the percent mass is determined by how many there are and the individual mass of those particles. Okay, so for this, we want to be able to accomplish a couple of things here. We want to be able to determine what's called an empirical formula. Okay, we want to be able to determine what's called a molecular formula. And we want to be able to do what's called, be able to determine the percent mass of a substance. Okay, now I'm going to start with the percent mass of a substance. It's the easiest. I'll start a new page here. All right, so percent by mass now of a substance. Again, I'm looking at a more of a microscopic molecular view of a substance. Carbon dioxide. Now, from this, I'll be taking the formula, which of course is a ratio of individuals. Okay, it's the locked ratio of numbers of atoms, 1 and 2, and converting that into a percent by mass. Pretty simple. So percent by mass is equal to the mass of X, whatever you're looking at, divided by total mass, times 100. Again, this is an introduction, just do one example and we move on. In class would offer more examples, more work, and more hands-on. But in this case, this is how it works. The sample size does not matter. So I'm going to use a sample size of 1 mole. Easiest for me to calculate. CO2, the carbon has a molar mass for 1 mole of carbon, and I will round occasionally for carbon. This is going to be, I'm going to go 12 grams. Oxygen, 16 grams, and there's 2 of them for 32 grams. Add it all up, we have 44 grams per 1 mole. You'll recognize this as the molar mass. Mass of 1 mole. Same calculation. So my total mass is 44 grams per mole, and we can also do it on an AMU basis. Then we have the 12 grams of the carbon. This is a percent mass carbon. 12 divided by 44 times 100 equals percent mass of the carbon. And then we have the percent mass oxygen equals to 32 divided by 44 and times 100. These two together should add up pretty close to 100% if you add them. But mathematically, 12 divided by 44 is 27 and a third, pretty close to a third, 27.3%, and then 32 divided by 44 equals 72.7%. 72.7%. Okay, and these are the percent masses of carbon dioxide. Now this is going to reign true no matter what from now until the end of the existence of our universe. Carbon dioxide has these ratios. So let's say, for example, I have a 1 gram sample of carbon dioxide. That means I'm going to have 0.27 grams of carbon, and I'll have 0.727 grams of oxygen. I could have a 10 gram sample. Again, I would have 2.7 grams of carbon, and I would have 7.27 grams of oxygen. This is a linear proportion, so we can use factor label, or we can use a proportion to figure out anything else off this matter. If I have 50 grams of carbon dioxide, how much carbon do I have, how much oxygen do I have? Okay, well, let's go with 50 grams, dot line, get rid of grams. And, well, in this case, there's a few ways I could solve this problem. Let's just do it this way here. Alright, so if we have 50 grams of this substance, there's a few ways we could do this. I could just set up a linear proportion, which would be, okay, well, if 27% over 100 equals, alright, this is total mass 50 over x. Cross, multiply, and divide. At this point, it would be 50 times 27 divided by 100 equals 13.5 grams. All right, so I have 13.5 grams of this guy is due to carbon. And you could do the same mathematics. I could also have just taken the pretty common way of doing it, just take 50 grams times 0.27 would give me my same value. At this point, I'll just take my 50 grams minus my 13.5, means I have the rest of it is going to be 36.5 grams of oxygen. All right, so this is a pretty common usage of percent by mass, which is a ratio. Okay. The next we'll look at is looking at empirical versus molecular. a little bit different situation, but it's the reverse of what we currently just did. I am going to run through one little example of this, and then you will be able to move on. But I'm going to use my percent by mass, which I just created last slide, and you come up with a formula. Okay, so for example, in this thing we have 27 and 73 we'll go with. Okay, and sometimes the numbers, we want to keep them as close as possible. In fact, let's just come up with a new one. Okay, so formula, take a percent by mass, and we'll come up with a formula. So I'm going to run through an example here, and the example will be I'm going to do N2O5 as my example. Okay, now before I run this problem through, I'm going to determine the percent by mass. So nitrogen is going to be 14 times 2 is 28, and then 16 times 5 equals 80. So this thing weighs 108 grams per mole. So the percent mass of nitrogen is going to be 28 divided by 108, and then the oxygen will be 80 divided by 108. And my percentages, 28 divided by 108 is 25.9%. So nitrogen is equal to 25.9%. And then we have 80 divided by 108 equals 74%. Okay, at 74, I have 0.07. And then the rounding, obviously it has some effects here, but oxygen is 74 point, let's go 0.1%. Okay, keep me at 100. All right, so now this is where our problem will start, and we eventually want to get back to that guy. Okay, so first of all, we want percent by a formula, and it's going to be what's called an empirical formula. Then we'll flip it to what's called a molecular formula. Okay, now empirical formula is defined as the simplest ratio of atoms. Okay, and a molecular formula is the actual ratio. An example of this before I solve this problem would be, a good example is glucose. Okay, glucose is C6H12O6. This is a ratio of carbon to 6, hydrogen is 12, and oxygen is 6. This is your molecular compound. It's a covalent bound molecule, and that's the actual ratio, 6 to 12 to 6. Whereas if I just look at this blindly, didn't just start analyzing it, I would only see carbon 1, hydrogen 2, oxygen 1. It'd be a 1 to 2 to 1 ratio, or CH2O. And in fact, this is known for a long time. Okay, this is called a hydrocarbon. Then they said, okay, we got carbon and we have water. That's what they thought for a long time, hydrocarbon. Nowadays, a hydrocarbon is something that has just hydrogen and carbon in it, but this is the actual where the name came from. Either way, so simplest ratio of atoms means I cannot reduce it down any further and keep my same percentages. So 1, 2, 1, just reducing it down, 6, 12, 6. Both of these compounds, this guy and this guy, would have the exact same percentages of mass. They would, exact same. So here we go. This is just how we actually get to these things, just changing around from mass to an actual number of particles. So we're going to go from percent mass to actual mass. And you can choose whatever size sample you want. I'm going to choose 100 grams. It's the easiest. So this is 25.9 grams and 74.1 grams. Then, once you're in mass, because each of these individuals has their own individual mass, convert to moles, which is number of particles, number of individuals. That's what we want to get to, number of individuals. All right, so it is a 1 to 14 ratio, grams to moles. This guy is 1 to 16 equals, and I will do the math here. We got 25.9 divided by 14 equals 1.85 moles. All right, equals 1.85 moles. And then we have 74.1 divided by 16 is equal to 4.63 moles. I would say that in these problems, small changes can have drastic effects on the outcome. So show your work. Be careful. So now we're in moles. Now this is the actual moles of your 100 gram sample. So we want to find the simplest ratio. So we're going to divide by the smallest. Now keep in mind, what this does is it sets the smallest to 1. That says if I have 1 nitrogen, how many oxygens do I have? So I'm going to divide this thing out by 1.85, divide by 1.85. I get a 1, and this thing, theoretically, for every 1, now we know the answer. We won't, in problems, you won't know the answer per se. But for every 1 nitrogen, we should get 2.5 oxygens. So 4.63 divided by 1.85 equals just almost exactly 2.5. Now, or I'm not going to write it like this, 2 1/2. Okay. Now, when you set your smallest one to 1, you get another bit of a problem here. If we were doing carbon dioxide, for example, we would now have a 1 to 2 ratio because the smallest one is in fact 1. But if your smallest one isn't 1, then you get a bit of a fraction. At this point, you would multiply by the reciprocal. Okay? Reciprocal of my fraction is 2. Both of them get multiplied by 2, and this gives me a 2 to 5 ratio. Half is probably the most common fraction that you will see. My empirical formula is N2O5. Again, this is a more complicated example. This right here is the standard path by which you would convert these things. Should be in your notes. Again, this is just one example. More to come in class. Now, let's look at the molecular formula. Okay. Now, the molecular formula is a little different. Okay. Now, that's the actual ratio. Now, I'll jump back and forth. Okay. Now, let's say, okay, well, if I want to go from the empirical formula to the molecular formula, okay. Now, at this one we had N. Well, we had let's just say we're doing glucose here. Okay. I'm gonna do. We know it's C6H12O6, and we know the empirical formula. If you break that down, would be CH2O. All right. What do we need to go from empirical to molecular, and what is the difference here? But either way, first thing, we need the molar mass. That is a piece of information needed. They both follow the same percent by mass, same ratio. So, for example, my empirical is CH2O. All right, and this thing has a empirical weight of being 12, 2, and 16, which is a grand total of 30 grams per mole. All right, now that's what I call the empirical weight. May not find that in a book anywhere, but the actual molecular formula is some multiple of the empirical formula. So, for example, C2H4O2, which would weigh 60, C3H6O3, which would weigh 90, C4H8 10O4, which would weigh 120, C5H10O5 would weigh 150, and C6H12O6 would weigh 180. So they would need to say you can't get the molecular formula without the molar mass. So it's okay, well, you determine the empirical formula, and oh, by the way, the molecular weight or the empirical or the molar mass is 180 grams per mole. And you can either step it down like this, or you can take your molecular weight divided by your empirical weight, which would be 180 divided by 30 and equals 6. This should be a whole number, and therefore this is inherently the multiple. You take your empirical formula, CH2O, multiply everything by 6 and get C6H12O6, and that would be your molecular formula. So I will point out one other thing about this that I think is important for the grand scheme of things. And again, more practice is needed to run through some of these calculations, but you should understand that when we look at empirical formulas, okay, versus say molecular, okay, this is the simplest ratio versus an actual ratio. By definition, all ionic compounds are all empirical. We have NaCl, we have AlCl3. You're never going to see Na2Cl2. This is not acceptable as far as writing an ionic compound. This is always in the simplest ratio. And why? Look at the crystal structure. We don't have molecules. We have what's called a bulk crystal. Okay? Bunch of cations, bunch of anions, no individual packages. Okay? And there's a ratio of cations and anions. By saying Na2Cl2 would allude to a possible package of 4 that is unique. That is not the case. All ionic compounds are ionic, are empirical by nature. Okay? Now, molecular is instituting, okay, well, okay, this is definitely a covalent compound. And, you know, a covalent compound like carbon dioxide, this is the empirical formula is also the molecular formula, just by happenstance, okay, by luck, as opposed to, let's say, C2H, I don't know, H6, okay, which is an organic compound. In this case, this can be reduced down to CH3, okay, which is fine, okay. Not every molecular compound has to be the same as its empirical, and not every empirical has to be the same as the molecular. So covalent compounds can vary, but ionic compounds are all empirical. Thank you.